Sure. We look at the rotational dynamics of rigid bodies. Now we are more or less familiar with the rigid bodies from our day-to-day experiences. Formally, we define a rigid body to be an extended object which the distance between any 2 points is not changing with time. So that means a rigid body has no elasticity. It is a three-dimensional object. It can translate and it can rotate about 3 axes. So using the Cartesian definitions, x, y, z, it can have 3 momentum, x, y, z, linear momentum, and also it can have 3 angular momentum about directions x, y, z, or rather it can rotate about 3 orthogonal axes. So as such, it has 6 degrees of freedom. Now in general, we will not be interested much about the translation at this stage. Rather, our focus would be more on the rotation. Suppose we have a rigid body and it is rotating about an axis depicted by a unit vector n, and it's moving with, let's say, omega angular speed. Now any point on the rigid body with respect to origin, let's say we designate this particular vector to be a. This could be written as a position vector r of that point too. So we just writing this to be the point a. So a vector, how does it change as we rotate it? If we are sitting on the rigid body, of course a does not change. With respect to the rigid body, the point is fixed. But we are interested in a description from what we call outside laboratory frame. So by laboratory frame, what we mean is we can choose to have an axis at the same origin as that of the in the rigid body. Maybe we choose the origin to be the center of gravity of the rigid body. Then with respect to the center of gravity of the rigid body, which is fixed, the point A is fixed and it's not changing with time. But for an axis system which has the same origin at the center of gravity of the rigid body, but it's not rotating with rigid body, it is fixed in the laboratory frame. So with respect to that, A is of course moving. So we have 2 coordinate system. One is the laboratory coordinate system, which is not moving, fixed, and sharing the same center, we would like to define another axis system which is fixed to the rigid body. So say laboratory frame, we call this to be x, y, and z axis, and then in the rigid body the body frame can have x prime, z prime, or y prime and z prime, another coordinate system. The only common point is the origin which they share, and these prime coordinates, or rather the rigid body, the body frame is actually rotating about some axis defined by, say, n caps. So in this case, it could be an axis about which the rigid body is moving. Now our target is to define the infinitesimal change in A, or rather rate of change of A, as observed from outside in the laboratory frame. So the way we do that, we draw this picture a little more clearly. Let us suppose this is the n caps, and in this plane of this board or this paper, we show the A vector. This is A. Now we would like to give a tiny rotation of an angle d phi about n axis. So we rotate A by an angle d phi. So the easiest way to do that is to take the component of A. Let's say we call this angle theta. Then A can be written as A cosine theta, which is this length, and plus A sine theta and perpendicular. So let n perpendicular be the unit vector perpendicular to n and in the same plane as which contains basically n and A. Now suppose we rotate A by an angle phi about n. Then of course, the new position of A would be here. So the vector which designates the change in A, we call it dA, let's say. dA is easy to calculate. dA would be simply A sine theta, which is this distance, into d phi. It's more like r d phi, r being the distance and this distance is A sine theta, the norm of this vector perpendicular to the n. So A sine theta d phi, and what about the direction? The direction is of course perpendicular to this plane, and the vector, unit vector perpendicular to the plane and into the plane is defined by n caps cross n perpendicular. That's it. So this is our change in A. This change, it can be written in an useful form in this way. Or we can also write we added this term, but this is 0. N cross n is always 0, so we can add it to whatever we had without changing its magnitude. So we will simply have the change in A given by the angle, the infinitesimal angle d phi into n cross A. So the rate of change is also now easy to calculate. It would be simply, but then rate of change of angle is omega. We already mentioned that. If we define the omega vector to be the product of the scalar omega, the angular speed, into the n caps, then we have a very useful relation that the rate of change of a vector which is fixed to the body frame is given by omega cross A, omega being the instantaneous velocity. You see, omega does not have to be constant. What I mean to say that omega could be a function of time. This d phi dt that gives you angular velocity, and this angular velocity, angular speed could be function of time, because nothing is specified about that. And not only that, this n caps could also be a function of time, in the sense that this omega vector in general could be a function of time. We are just calculating this by looking at an infinitesimal change at a particular time. So in this equation, everything could in principle be function of time. Omega could be function of time. Now we move on to the next important part. What if A is not fixed? We just mentioned that A is fixed to the body frame, and if it is, then from outside, from the laboratory frame, the rate of change of A is given by omega cross A, which is essentially coming from the rotation of the rigid body. A is fixed in the rigid body. And now we say that A is not, A is changing. So, I mean, it's more like we have this rigid body, and here is our omega. The rigid body is actually rotating about this axis. And then, with respect to someone outside, this point A, which is changing, there are actually two changes. The change with respect to the body and the change of the body axis itself. So that means from outside, whatever we see, suppose we designate that as lab. This is our laboratory frame. We would say this would be equal to let's understand this a particular line. Let us suppose the rigid body is not rotating, it is fixed. It's fixed in the laboratory frame, it's not moving. In that case, with respect to the body axis, that is with respect to the rigid body, a tiny change in A would be same as observed in the laboratory frame. After all, both the frames are identical in the sense the rigid body is not moving, a laboratory with respect to laboratory frame, which is our inertial frame. So both frames, their axes are fixed, so there's no rotation at all. So in that case, laboratory frame change would be equal to the body change in the body frame. And this term, this third term, would be 0 in that case. There's no rotation. On the other hand, for a fixed object, meaning A is not changing with respect to body frame, then this dA body would be 0 and dA rotation would be only term which remains. But in this dA rotation we calculated just now. So we know that it would be like d phi, something like this. We just calculated that. So the rate of change with respect to laboratory frame is now easy to define. Is given by that's it. It's a very useful result in the sense that we have to simply add the two rate of change. One is with respect to the body frame and the change of the body frame. Now, change of the body frame is coming purely because of the rotation, and which gives a contribution omega cross A. So, in general, one can say that we can simply define an operation. It holds true irrespective of A, the particular vector, that rate of change ddt with respect to laboratory frame is given by ddt with respect to body frame plus omega cross whatever we are, whatever, I mean, the change of whatever we are interested in. Okay. Of course, we are talking about the position vector like quantity. If that is, then let's start with the position vector itself. I mean, how does the position vector of a point on the rigid body, how does it change in the laboratory frame? Well, that would be straightforward. dr dt left frame should be equal to dr dt the body frame plus omega cross r. How does this relate to our everyday experience? It would be like this dr dt. Let's say our rotating frame is the earth itself. So we are on the earth, and then with respect to earth frame, something which is moving, let's say a train, a fly, aeroplane, anything, a cricket ball. So with respect to earth, we have to calculate this vector. That would be the change in the body frame. But then earth itself is moving. So somebody standing outside, maybe with respect to the sun, or any observer defined anywhere in the outer space, would see that this omega cross r, which is coming from the rotation of earth about its own axis, so that change plus the change with respect to the earth. So we have to add the two contributions and we get everything. We can designate it. We can call it some VL, L for lab, and this is dB, this is B for body. I mean, after all, rate of change of position vector is nothing but velocity. So we have one useful relation in terms of L, B, and then omega cross R. Then what about acceleration? Well, acceleration is a little more involved in the sense that what we would like to calculate is ddt of VL, but this ddt must be the ddt of lab. This is what we are trying to calculate, that from outside how does the acceleration look like. Well, ddt of lab, we just now expanded that would be ddt of the body frame plus omega cross, and this must be acting on VL. But then VL has been defined to be, in the above equation. So we write it down, everything, that ddt, just we substitute this expression into VL to get ddt of the body of VB. And then we have omega cross VB plus we have these are all our terms. So we will simplify it. First of all, the left side, this is the rate of change, this is acceleration as measured by the laboratory frame. I've measured in the laboratory frame, so we will simply call it AL. Okay. Now the first term in the right hand side is the acceleration as measured in the body frame. So this is the body frame acceleration. Omega cross VB is one term, and okay, we just write it down. Now we have a derivative acting on this cross product, so we will simply have omega dot. Here the dot must be understood in the body frame. So one advantage is in the right hand side, everything is in the body frame. Okay. Now plus R dot. R dot is V body by definition because the ddt is in the body frame, and plus we have omega cross R. So this is body frame plus 2 times okay, so we got it. Now a very useful quantity is actually this. The acceleration in the body frame, we would like to calculate the acceleration in the body frame in terms of the acceleration in the laboratory frame. I'll explain, what I mean. It might seem that we are mixing the two cases in the sense that I'm trying to write acceleration in the body frame using this acceleration in the laboratory frame and all other quantity as measured in the body frame. But what does it actually mean? I'll explain that. Okay. So we have all those terms, but they come with a negative sign. That's it. Now, the acceleration in the laboratory frame, this is more like a, like an external force divided by mass. What I mean to say, this is an inertial term, or this is the term which has nothing to do with the rotation. For example, on the surface of Earth, we are trying to describe the motion of an object, and would like to write down its acceleration, the correct form of its acceleration. So what we do is we say, well, the acceleration of this object would be the acceleration measured in the laboratory frame, which means acceleration measured had there been no rotation. Now, acceleration measured had there been no rotation on the surface of Earth, it is straightforward. It would be, we know it would be g in the negative z direction. That's it. So, but to that particular value, we must add all these forces, and these are our so-called pseudo forces. In the sense they are not real forces. It's they arrive here simply because the Earth is rotating. So with respect to us, when we try to describe the acceleration of an object, then because we are on the Earth, we are in a rotating frame, we will have to add a certain fictitious forces. Now this you have already encountered, in the sense that in your earlier treatise on motion, you definitely encountered a situation that when you go to an accelerated frame, you have to add a fictitious force. Usually, whichever direction the acceleration is taking place, the fictitious force would be acting opposite to that. This is particularly true if you go into an accelerating elevator, for example, which is going up. In that case, the acceleration due to gravity would be there, g, but on top of that, the force due to gravity would be mg downward, and moreover you will also have a fictitious force ma acting downward. Now, these are similar fictitious forces, except their directions are quite complicated. It's not straightforward that they would be acting which way. So, we will analyze that. In fact, this relation is so important that we would like to analyze two very specific cases. But before that, let us give some names of this fictitious force. This this is Euler force. This is called Euler force. Commonly we don't encounter it, simply because in case of Earth's motion, the omega dot is 0. There is no torque acting on the Earth which is making its the angular motion, angular frequency about its own axis. It's not changing with time. So it does not appear, but in general, for a rotating frame transformation, such terms appear, and it is called Euler force. This one is called Coriolis force, and this is centrifugal force. Now let us look at their directions. Okay. In some simple cases, let us suppose this is omega axis, and then let's say we are interested in this particular point. This is the position vector R. Then omega cross R would be along the direction which is into the plane of the page, and then omega cross R, omega cross that particular, so that means omega cross R, this would be along the negative R, but we have a negative sign, so the fictitious force would be acting outward. So if we are in the rotating frame, then we will see a particle at R will experience a fictitious force given by this term at times m, of course. We are talking about fictitious force. Without m, this is the fictitious acceleration, which is fine. We understand that it must be acting outward. Now, what about this omega cross B? We don't have to write the B all the time, simply because now we are assuming that our descriptions taking place only on the inertial, in the rotating frame along with the rigid body. That's the rigid body axis, body frame. Okay. So as such, let's say this velocity, it is going out. So r dot is going out and it is along the direction of r. So what I mean to say, let's say the direction is proportional. So actually it is more like this is what I mean. The unit vector along r and the unit vector of v are the same. In that case, the omega cross b would be along this direction, but we have a negative sign in front of that. So the fictitious force, will get the fictitious force, it would be along this direction, the direction shown by the arrow. Of course one has to multiply this by the mass and then you will get it. So it would be towards the right. So if it is towards the right, that means if you have a particle thrown outward, then it should move towards the right. That is what is indicated by this force. Yes. So at this, so it's clear that we have got, I'll try to summarize the results, that rate of change of the velocity of an object which is being defined in the rotating frame, it should be calculated by the inertial contribution, which we say the acceleration calculated in case of no rotation. So which in this case we have given as an example, this is the acceleration due to gravity for r. And on top of that, one must add a series of fictitious forces, which is purely coming from as an effect of rotation. So if we say omega is 0, then of course the rotation vanishes and all such fictitious forces vanishes, and we are left with the inertial description, which is good, what we expect. Now we shall consider two cases in the sense that we would like to consider the manifestation of the Coriolis force. We are not so much interested in the centrifugal force at this stage, at least for the motion of projectile on earth. The centrifugal force is not significant. It does not alter things much, but Coriolis force could be significant. and would like to discuss the effect of Coriolis force on the projectiles and on other motion on the surface of Earth. We mentioned that we would like to look at some examples of the application of Coriolis force, particularly for projectiles, the motion of the projectiles on the surface of the Earth, and also we would like to look at the effect of Coriolis force on natural objects. I mean, natural objects in the sense large objects, for example, the motion of air or the rivers. I mean, how are they affected? So to do this, I mean, first we would like to quantify Coriolis force. I mean, using the regular coordinates suitable for description of the objects on the surface of Earth. So what we do is we draw a diagram where we show a part of the Earth's surface, and let us suppose this is the center of Earth, and this vector represents the omega. So I mean, it's basically, one can imagine this is Earth, and what we are trying to do is to draw a patch on Earth's surface. So from this center, let's say the vector perpendicular to Earth's surface, let us choose that to be our z-axis with unit vector k, and then what we do next is we have to choose the x and y. So we do it this way. Let us suppose, I mean, at this point the vector parallel to omega is drawn, and then in the plane containing, I mean, first we define, I mean, the co-latitude of this point. Let's say this angle with respect to vertical, which is the axis about which Earth is rotating. So I mean, I am drawing the co-latitude here too, to make you understand what I am trying to do. The angle describes the orientation of the local vertical with respect to the axis of rotation. Now these two vectors, their angle is theta, the same as the co-latitude of the point, and then it is clear that the component of omega along the local vertical would be omega cos theta. So I can write omega as omega cosine theta plus. Now we would like to look at the other component. Well, if the component of omega along k is omega cos theta, then perpendicular to k it would be omega sine theta, and that component we would like to take its further projection into the local x and y coordinate. So this particular patch, suppose we are looking down along this patch along the k, so a negative z axis, meaning we are looking down this direction, then we will see the patch of a flat space around the point, and the k is straight towards us. So the component of omega on the ground would be omega sine theta, Now let us suppose we choose our x and y coordinate such that it makes an angle phi with respect to the local north. Well, from this point, the straight outward, meaning this is the plane of the paper, from this plane at this point, the vector normal to this plane is the k caps, the local particle. And then the way we have drawn the vector here is same as the vector shown here. And this being the north pole, so essentially this vector that I am drawing now is pointing towards the local north. This would be the south. So the local north, with respect to that, let's say the x-axis makes an angle phi. So in that case, the component of omega along the x-axis would be omega sine theta cosine phi. And the other component this completes the projection of omega using local x, y, z axis. Okay. Now we take up one example. For example, suppose we are considering something. It could be a projectile, a bomb, or a rocket, or we are just considering air moving towards, let's say, x-axis. So we are considering some motion which is roughly horizontal at a given time along the x-axis. Then what would be the Coriolis force on this particular object? That is easy to calculate. We have already found that fictitious force would be given by and in this case we are assuming that at any given point, let's say v is along x-axis, magnitude being v naught, then this force, which can also be written as, would be equal to the determinant which would be so we see the Coriolis force on this object has two components, one along the vertical direction, the other along the negative j direction. So that means negative y. So it would be twice m v naught omega cosine theta Now, as we mentioned, when we consider the motion of a particle, then we will compare the Coriolis force along the z direction with other forces along z direction. Other forces along z direction being gravity. The gravity is significantly stronger than the Coriolis force. How do we verify that? Well, in this expression, You see, we can compare the gravity, which is mg. We know the value of g. So we will compare essentially g with v naught omega sine theta sine phi, and with the factor 2, of course. Of this, the most important value is omega. Omega is Earth's angular speed. Now, Earth's angular speed is significantly small. So, as a result, for all practical velocities, suppose we have a particle which is typical velocities are like hundreds of meters per second. I mean, assuming we are going as fast as the velocity of sound, typical speed of bullets or projectiles. Or in case of air or a river motion, this product is usually negligible compared to g. So as a result, the k component does not change the motion significantly. But what we have is, earlier we did not have any force along the transverse direction, but now we have one, and the direction being along the negative of j as long as cosine theta is positive. So let's say we are considering theta less than 90 degree, less than equal to 90 degree, and obviously for that what we have is cosine theta positive. So as such, the force, Coriolis force, would be along negative y-axis. So you remember in the local geometry, this being the x-axis, and I will also draw the local north, south, east and west. This was the direction of the particle. Now, Coriolis force says, our calculation shows that it will deviate because there is an acceleration towards the negative y-axis. So it will have a component, it will accelerate along this direction. So as such, the particle will deviate from its straight line and it will bend towards its right. In southern hemisphere, where the theta is more than 90 degree, cosine theta is negative. So as such, the product would be positive. So in southern hemisphere, the acceleration would be towards the left. Now suppose we have some air current. So if it is going along, say, this direction, and we are looking at the surface of the earth from the top, so it will deviate towards the right. Similarly, any current which is coming down, from, say, northeast, will also bend towards its right. So all currents which are going in straight line will bend towards the right. As such, we will have a circular motion. If we have a cyclone kind of situation, the circular motion will always be anti-clockwise. Similarly, in the southern hemisphere, where the currents are bending towards left, the cyclones will have a clockwise motion. We know this, for many years now. Just wanted to see this strictly from the expression of Coriolis force. And this also shows that in northern hemisphere, the typical situation that the right bank of the rivers suffer from more corrosion. That also happens due to Coriolis force. Now, how do we quantify the deviation from the straight line due to the Coriolis force? We would like to see one example for vertically falling object, or vertically, the objects which are moving vertically. Okay. In that case, let's suppose, for simplicity, our object is going down. So suppose it starts from rest, an object which is released from rest from certain height z naught. and then it is simply falling on the ground. Had there been no Coriolis force, it would come down straight and hit exactly vertical point below. But then on the surface of Earth, if we carry out the same motion, meaning we release it from a height and see where does it land. Suppose we take this object vertically high up, just exactly above this point, and release it. It is clear from the Coriolis force that it will not hit the ground at this point. It might be deviated towards right or towards left or other directions. So we would like to find out how much would it deviate and what would be its expression. Okay, so let's calculate that. First of all, we calculate the Coriolis force, of course, once more. What we do is, at this time we choose, by the way, the phi to be pi by 2. So which means this is our x-axis, this is our y-axis, and z-axis is the local vertical. So twice m v cross omega would be x component, y component, z component, and we will have, omega cosine theta. No, omega cosine theta will be this component. So we'll take the omega out and only write the theta part in, and then we have omega sine theta cos phi, but phi being pi by 2, that would be 0. So this term is 0, and we will have sine theta sine phi. Sine phi is 1. So this is our Coriolis force, which would be twice m omega Vy cosine theta minus Vz sine theta. That would be along the x-axis, and then along the y-axis we will have and finally right angle, move it towards the right, and then along the vertical direction that's it. So for the object which is falling down, this would be the fictitious force acting on it, apart from other inertial forces. And of course, like we mentioned, we are ignoring the centrifugal force. We are ignoring the centrifugal force because it contains the term omega square, and we mentioned that omega itself is quite small, so omega square is negligible. That hardly changes the acceleration due to gravity, so we will not consider that. And moreover, in case of Earth's motion, the Euler force, which involves the rate of change of omega, is also 0, so that also does not feature in the equation of motion. So equation of motion for an object which is falling down would be m v dot, and would be equal to the inertial force, which is the gravitational attraction towards the local vertical, negative local vertical, downward essentially, and then the Coriolis force, which we calculated above. So we write down the equation term by term. The m cancels from all sides, So we will have the equation of Vx would be we just took this term, and similarly the rate of change of Vy would be and this would be right. So these are our equation of motion for the object falling under gravity and experiencing the Coriolis force. So of course, I mean, this equation is fairly complex, but we can certainly make a couple of simplifying assumptions, which is which does not I mean, which is all right. I mean, in the sense that first look at the lost equation. So we have two terms to compare. One is g, and we know the value of g, which is 10 meter per second square, and we have omega and Vx. Now you see the Vx is very small. The Vx is building up because of the Coriolis effect. So without Coriolis effect, Vx is 0, and with Coriolis effect, Vx is typically of the order of, I mean, like centimeter per second. Now that when you multiply that with omega, Vx is proportional to omega, you can verify from the equation above, and then we are multiplying Vx by omega again. So this term itself is proportional to omega square. But then we already mentioned the omega square terms are negligible compared to g. So if that is the case, then this term is significantly small compared to g. So we shall take our last equation to be approximately equal to the. So that means we are saying that vertical direction motion is not essentially being affected by Coriolis force, at least by not much. And then what does it give us? The solution. The Vz would be, I mean, like minus gt plus some constant k. But at t equal to 0, the particle was, or the object was released from rest. So Vz at t equal to 0 must be 0, and that means the k is 0. So we have basically Vz, which is z dot, the rate of ascent of z is minus gt, and this if you solve, you get, where of course at t equal to 0 we are assuming that the particle was released from a height z naught. Okay. So this is our equation. Also, I mean, from this equation we say that if we are looking at the situation where the particle is hitting the ground, so that means z is 0. So time it takes to do that can easily be calculated from, and the total time of flight would be and we'll take a square root of course. Okay. So this is the total time it takes for a particle to fall down. We already know that. Okay, so we are assuming that Coriolis force is not changing this time, not by significant amount, which we already argued about. Now, in the equation of x and y, let's look at what are the significant terms. we can already see that Vy is proportional to omega square, because Vx being proportional to omega and this term is being multiplied by omega, so Vy is the acceleration along y is proportional to omega square, which we argued the small and could be ignored. What about x? In the x we have two terms. One is again proportional to Vy, and then Vy, the rate of change of Vy is proportional to omega. So if we could integrate, it would be proportional to omega again. So this term, by the similar logic, the first term would be negligible compared to the second term. The second term is Vz, and we have seen the Vz is approximately is equal to minus gt. So it's not proportional to omega, it's largely dominated by the acceleration due to gravity. If that is the case, then in the equation of Vx, the most significant term would be the second one, and we will keep that. So we will have Vx dot to be equal to I'm just substituting the expression of Vz in this expression to get right. So which means if we integrate it once, we get, that's the Vx, and if we try to calculate x, which is integrating the above equation once more, this is the solution. All the integrating factors are 0 for the simple reason that at t equal to 0, the velocity along x-axis was 0, and also we are assuming that the dot over which we are dropping it, this is the origin. I mean, no harm done because no other objects involved, so only one particle is falling, and that could be origin. If that is the case, that means initially at t equal to 0, x was 0. So when it goes down, what is the total displacement due to Coriolis force? What is the value of x when it hits the ground? Well, that would be just t cube, and t cube being given by this, and with sin theta of course. So what we find is x is definitely positive, so which means the earth which is moving it's rotating from west to east. Then if you drop a particle from a reasonable height, from some height, then when it hits the ground, it would be deviated towards the east. X is, the direction of x is towards the east, so particle will be deviated towards the east. Okay. And we just calculated roughly the magnitude by which it will be shifted. Okay. So this is one interesting result. So that means, suppose this is east and west, and the particle is being dropped. So instead of coming down along a straight line, it will deviate slightly towards the east. Okay. Now suppose you try to argue, in these equations we are ignoring the y, but suppose we don't actually ignore anything, suppose we keep everything and then try to solve it, then definitely there would be a deviation along y. Yes, of course there would be a deviation along y and along x. Then what would be the numbers? The numbers are slightly more cumbersome to calculate. We need to plug in the value of omega, which we can definitely calculate knowing the radius of Earth, which is 6,400 kilometers, and then Earth rotates about its axis in 24 hours. So period being 24 hours, one can easily calculate omega. So suppose you plug in that value, plug in the value of g, and then after solving this equation, you will find typically the x. Suppose we are dropping a ball from a height of, say, the height of, say, Eiffel Tower, which is, I believe, around 300 meters. So if we drop it from there, I think the deviation along x-axis would be of the order of like millimeters to centimeter, and the deviation along y-axis would be negligible, in the sense it will come out to be less than millimeters, which is very difficult to experimentally determine, because there are other factors like air drag and other stuff, because of which it hardly comes down in a straight line. So it's very difficult to measure the deviation along y, but the deviation along x is clearly measurable. It has been measured, and this expression more or less works. So our approximations were not so bad.